So, we have seen that the electromagnetic waves in free space, the electric and magnetic field vectors, how they are related, how they are oriented, what is the relation amongst them. And now, we will see the polarization property, a very interesting property of the electromagnetic waves, and that we will first take up in the case of electromagnetic waves in free space. So, let us consider a situation that the wave is propagating along z direction. So, you can write that the k vector as z unit vector into k, where k is the magnitude of the propagation vector. And you also assume that the electric field E is along x. So, in the earlier occasion also we assumed the same convention that the propagation is along z direction and the electric field is oriented along x. So, having known that, we can write the electric field in this way, E equal to E 0 sin omega t x unit vector, because the electric field vectors are along the x direction. Now, by writing this equation, we have considered the imaginary part of the complex vector solution, that is E equal to E 0 e to the power of I omega t minus k z. So, in the rest part of the discussion, we will consider only in the sine cosine form. If I have considered E equal to x unit vector E 0 sin omega t minus k z, then the B will be oriented along the y direction, we have seen as well. So, B equal to y unit vector V 0 sin omega t minus k z, and you can see from these two equations that E and B are in phase. This situation, the orientation when the electric field is restricted only in one particular coordinate direction and magnetic field is also restricted in one particular coordinate direction, such a situation of the electromagnetic waves called that linearly polarized wave. So, this is how we represent an x polarized wave. So, the situation where the electric field vectors are along the x direction, we call such a wave as an x polarized wave, x polarized linearly polarized wave. Then we consider a situation where, because our intention is to study the other variation, the other properties, polarization properties. So, we consider another situation where the wave is y polarized. In that case, how do I write this wave equation? E should be equal to y unit vector E 0 sin omega t minus k z, and B will be equal to minus k minus x unit vector B 0 sin omega t minus k z. Look at this figure, you see y, along y the electric field is oriented, and along minus x you have the electric field oriented. So, that means this y polarized light means the electric fields will be along the y direction and magnetic fields will be along minus x direction. So, by that convention, if we consider this situation, then we can take up this particular situation that we add an additional phase of pi by 2 to this wave, because we started off with this wave which has a 0 at z equal to 0. So, this is a sine wave, but if I add a phase of pi by 2 to each of the waves, the wave will advance by a phase of pi by 2, and the other orientation of the electric and magnetic fields will remain same. So, in that case, how do I write this equation? For the electric field, everything remains same, I just add a phase of pi by 2, and for the magnetic field as well I add a phase of pi by 2. As a result, you can write this equation in this form: y unit vector E0 cosine of omega t minus kz, and for the magnetic field we can express as minus of x unit vector B0. Indeed, this has become a cosine function, earlier it used to be a sine function. Now, recall that Maxwell's equations are linear, and a linear superposition of their solutions, the x polarized wave and y polarized waves, will be considered, and that is also valid when I take this x polarized light which I have considered first, that is given by the set of these two equations, and the y polarized light which I have considered by which are given by the set of these two equations. This is y polarized light, but there has been an advancement of phase by pi by 2 from the starting point. So, at z equal to 0 we will consider what happens to this phase, but before that we will have to consider the superposition of these two. So, the linear superposition of this x and y polarized waves will give you the total electric field E equal to this x polarized part and x component of the x polarized part and y component of the polarized part. Similarly, for the magnetic field we can write these equations. So, basically these are taken from these two. I just take the linear superposition of E and this E. So, this quantity plus this quantity put together, and likewise for the magnetic field this quantity and this quantity will be put together to get this equation in this form. Right. Now, we will consider what happens when we see the wave at z equal to 0. So, at z equal to 0, I put this z equal to 0. So, this becomes 0, this becomes 0, and altogether in all 4 places it becomes 0. So, it becomes only a time dependent oscillating electric field. And indeed it is true, at a given point for a travelling wave electric field vectors are just oscillating at the same point, and the oscillation is purely simple harmonic type. So, E x can be represented as E 0 sin omega t, and U I will be represented as E 0 cosine omega t. And similarly, for the magnetic field you can write this equation. Now, look at this situation that if you look for the amplitude of the total wave, you can write, because if you take the square and add them, you get this equation E square, the resultant amplitude square will be equal to E 0 square, which is constant, and this equation basically gives you it reminds you the equation of a circle E x square plus E y square equal to some constant square. And the same thing we will have seen in the case of rotating magnetic field and many other occasions. E x square plus E y square equal to E z square will be represented by a circle where the radius of the circle is the amplitude of the resultant wave. For the case of magnetic field, it will be a circle of different magnitude B 0, because B 0 and E 0 they are related by a factor of c, which is the velocity of the electromagnetic wave. So, they will describe a circle, and the superposition will give you that the tip of the electric field and the magnetic field vectors rotate on the circumference of a circle. This particular situation, this particular orientation of the electric field or the magnetic field in a travelling electromagnetic wave is known as the circularly polarized wave, and this is of tremendous importance for various parts of optics, and also it is very interesting to analyze different situations for circularly polarized light, linearly polarized light, their production, their analysis, and these are all very interesting findings. So, we have seen that the tip of the electric field vector is describing a circle, but there is an aspect that we have to consider whether it is rotating in the clockwise sense or in the anti-clockwise sense. So, that should be decided by the orientation of the electric fields and the magnetic fields, their relative orientation of the electric and magnetic. We will consider a particular situation. So, the electric field vector, the tip of the electric field vector, when you consider different positions along the z axis, they will be advancing in the form of an helix. So, E and V vectors trace an advancing helix as it is shown here, and this situation is the true three dimensional picture for a circularly polarized wave. Even though it describes a circle at one plane, at one position, which is one plane which is perpendicular to the z axis, but the tip is advancing because the wave itself is advancing. So, the tip will be described, we will be describing the trace of an helix. Next, we consider this situation, that how we analyze whether it is the tip is rotating, tip of the resultant electric field is rotating in the clockwise sense or anti-clockwise sense. In order to do that, we consider that at z equal to 0, what happens to this electric field and the magnetic field. Let us consider the electric field E x equal to E 0 sin omega t and U I equal to E 0 cosine omega t. Now, at time t equal to 0, that is at the initial time, and the position is also at z equal to 0. For all the discussion, we have considered that the position is fixed at z equal to 0. That is why we could write the equation E x equal to E 0 sin omega t, U I equal to E 0 cosine omega t. So, at z equal to 0, you get that E x equal to 0, but U I equal to E 0, because cosine omega t will become 1, and you get that because U I equal to the maximum amplitude E 0. So, this is your U I. So, the orientation of the resultant electric field is along this. Then next we consider at time t equal to pi by 4 times 1 upon omega. So, at this time, if I substitute this value of t in this equation, then this will give you E x equal to 1 by root 2 E 0, because pi by 4 into 1 by omega will give you only pi by 4. So, sin pi by 4 will give you 1 upon root 2. So, E x will have the value 1 by root 2 E 0, and U I will have the value 1 by root 2 E 0 when you substitute this t value here, because cosine and sine at 45 degree will give you the same value. That means, if you take the resultant of the electric field component and the magnetic field component, that is E x square plus E y square, which will be equal to E 0 square, their position will now be along this direction. Next, if you consider twice this time at an interval of pi by 4 into 1 by omega t, then E x, because now this quantity will become 1, whereas this quantity will become 0. So, the result is that you will get E x equal to E 0, but U I equal to 0. That means, E x, the entire amplitude is along the x axis, that is along this direction. So, it tells you, if you proceed further with the same analysis with the values for intervals of pi by 4 1 by omega t, you can see that the electric field will next time orient along this direction, and next time it will come along this direction, and so on. So, that means the tip of the vector is now rotating in this sense. So, this is called a right circularly polarized light. So, we could very nicely explain that how the tip of the electric field is rotating on the circumference of a circle and representing a right circularly polarized light. So, looking at the source, this is how we distinguish the right circularly polarized light and the left circularly polarized light. So, looking at the source, E of the wave coming towards you is seen rotating anti-clockwise. The wave is circularly polarized light. And looking against the direction of propagation, that is looking at the source, if E is seen rotating in the clockwise sense, the wave will be left circularly polarized light. So, in the earlier case, what we have seen, the electric field vector is rotating in the clockwise sense, but this is away from the source, looking against the source, looking towards the source, this will be right circularly polarized light. Let us next consider a situation to look for left circularly polarized light. For that, if you consider the combination of x and y polarized waves in this form, that is E equal to E0 cosine omega t, which is the x component, and y component will be minus E0 sin omega t minus kz. For B, similarly, we will have a cosine for the y component and the sine for the x component. Then this equation, if we do the same analysis, that is at time at z at position z equal to 0, we write down this equation for this, which will be E0 cosine omega t, and this will be E0 sin omega t. For the magnetic field, this will be B0 cosine omega t and B0 sin omega t, but this is minus and this is plus. So, we can take the superposition and we can find the resultant of this wave at different positions, that is at t equal to 0, t equal to pi by 4 into 1 upon omega and 2 pi by 4 into 1 upon omega and so on and so forth. Then we can see that the tip of the electric field is rotating in the anti-clockwise sense, in the counterclockwise sense, and such a wave will be referred to as a left circularly polarized light. When the amplitude of Ex and Ey are not the same, because so far throughout the discussion we have considered that the electric field amplitude and magnetic field amplitudes, electric field component, the magnitude of the electric field for the x component and that for the y component, they were same. Then it was a circularly polarized light, because the contributions from Ex and Ey were same. But let us suppose in a situation where the Ex and Ey they are different, then instead of a circle, now the tip of the electric field will describe an ellipse. The ellipticity will depend on the relative magnitude of the Ex and Ey component, and in the same way the tip of the electric field will advance as along the direction of propagation. So, the ellipse will now represent the circle in the case of elliptically polarized, and such a situation is called elliptically polarized wave. So, we have seen in this discussion that starting from the basic electromagnetic wave equation for free space or vacuum, how we write the solutions, plane wave solutions, and from the plane wave solutions we use the Maxwell's equation, the first equation, the second equation. From there we arrive at that the dot product of k and E, k and B, they are 0. So, meaning that k and B will be perpendicular to each other, E and k they are also perpendicular to each other, but it is not sure till then that whether E and B are also perpendicular to each other, and for that a more rigorous analysis we use that the Maxwell's third and fourth equation, the curl equation, where we could constitute the cross product of the k and E and also the cross product of k and B to show that all the three components, all the three vectors, that is the electric field, the magnetic field and the propagation vector, three of them are oriented mutually perpendicular to each other, and we also found the relative magnitude of the electric and magnetic field. They are connected by a factor c, which is the speed of light in the case of free space. Then we analyzed how the electric field is oriented and how we achieve the linearly polarized light, circularly polarized light, and we have also seen if the amplitudes of the x and y component of the electric fields are different, then we end up with an elliptically polarized wave. Thank you.